talking about how, like, the sort of the equations that govern how capacitors charge up. So remember we mentioned with the demo, Alan had to like spend a little bit of time charging up those capacitors. It didn't happen instantaneously. So we're gonna look at like how do capacitors charge up and how do they discharge? Okay, because it doesn't happen like instantly. Okay, so we're first going to talk about discharging circuits. And we're going to apply the same loop rule that we did with the Kirchhoff law part. Okay, so using Kirchhoff's law, so let's say you've got the following situation. We take a capacitor, and we've already charged it up. We've charged it up to some like charge, which we're going to call Q naught. And we place it in the circuit, and then we close the switch. What do you think happens as soon as, so we've got the capacitor, it's already charged up, right? I've charged it up like somewhere else before. And then I bring it over, and I put it into this circuit, and I close the switch. What do you think is going to happen to the capacitor? It'll discharge, right? The current will, or the charge will leave the plates, and it'll go through the resistor. Okay, we can apply the same junction rule to this situation as we did to the circuit that we just had with the two resistors in parallel. Yeah.
How does a charged capacitor act different from a battery?
That's such a great question. It doesn't really. So the question was, how does a charged capacitor act differently from a battery? So, I mean, it's different in the sense that like a battery it's the chemical reaction that is creating the charges that flow. So that's one way it's different. The other way is like once this capacitor is discharged, it's discharged. It's like it's not like the current bleeds or the charge kind of bleeds off it, and then it doesn't have any more. Like unlike a battery where like you put it into a circuit and it'll go for a while. Like this, once it discharges, like that's it. So like if this resistor was a light bulb, right? Like let's say R2 was actually a light bulb. What do you think would happen? Like so I put the capacitor, I've got the capacitor, I've charged it up separately, like privately. I put it into this circuit. What do you think is going to happen to the light bulb? It's going to get really bright and then dim and then turn off, right? So like the current, like at first there's going to be a lot of charge going through it, right? As the charge from the capacitor goes through the resistor, right? And then the current's going to drop off, and it's going to drop off actually exponentially, and so the bulb will get dimmer and dimmer. And this is actually something that I did a lot of when I was first learning this. Remember, I'll find this next time. There is a FET simulation that you should look at. So if you just Google capacitors FET simulation, remember I showed this to you when I was showing you the equipotentials? There's another variation that is excellent. Right, you can build a little circuit, like a simulated circuit, and you can connect like virtually, like a bulb to a capacitor, charge up the capacitor, and you can see exactly this. But that's a great question. Okay, so we want to know, using Kirchhoff's law, we want to find an equation for the current in the capacitor in terms of like Q and all of the other things that we care about. Okay. So we're going to use Kirchhoff's laws, right? So let's draw, we're going to draw a loop, just like this, okay? So remember, I think the thing here is that this has an initial charge. Like we're charging it up ahead of time, okay? I think if you don't realize that, then this is really confusing. So you close the switch, the charge, so the current is going to go like this way, and then this way, and then this way, right? And then I've drawn my loop there, okay? So using Kirchhoff's law, what would it look like? I know that the loop rule says that the change in potential all the way around the loop has to be 0. So by loop rule, okay, I know that if my loop is going in the same direction as the current, then what's the convention? Let's look back at that page, all the way back here. If my loop is going in the same direction as my current, then the potential drop, or the potential change, is negative Q over C. Okay, so that's what I'm going to start with here. Okay, so I'm going to say, like, across here, across this component, the potential drop is going to be negative Q over C. Okay, and what about, and then this switch is just a switch. Just think of it as a straight wire, so there's no potential change. What about through the resistor? Minus I times R2 equals 0. Okay, so I, therefore, equals negative Q over C times R2, right? Just rearranging that equation. Okay, so that should make sense. And you could actually graph it, right? So there's this equation called the discharging equation, which we would need to do quite a bit of calculus to be able to derive, so I'm not going to do that for you. This is just basically the charge on a capacitor as a function of time. So remember we said it's not a linear thing, as a function of time. Okay? So Q naught is like the initial charge that we had on the capacitor. Remember, that's what we set up here. Q naught is what we started with. So it has, this capacitor had an initial charge of Q naught, right? And when we discharge it, the charge, I could figure out how much charge I have at any one point in time by substituting time into this equation, right? So at t equals 0, how much charge do I have? Yeah, Q equals Q naught. Does that make sense with the equation? So if t equals 0, so I would put 0 in there. I made it so that you can't read it. But if I substituted like t, if I substituted 0 in for t right there, it would be like e to the 0, which is 1, right? And Q naught times 1 is just Q naught. So at t equals 0, Q equals Q naught, and that's actually what you see here. Okay, and then as time goes on, like the charge drops off exponentially. And Alan has a very nice demo that I'm not going to have time to do, but I'll do it at the beginning of 2 weeks from now. Okay, where you can actually see this exponential drop off. There's a thing called a time constant. Okay, so this is denoted like tau, and it's the time constant. It's just called time constant. Okay, and it's the amount of time that it takes for the capacitor to discharge to like Q naught over E. Right? So like this is Q naught over E. E being like the natural log number. Okay, so it's the amount of time that it takes for the capacitor to discharge to like this value. Okay, it's just a definition. Okay, so let's just kind of explore this. So if the discharging equation is Q naught times E to the negative T over the resistance times the capacitance, okay? So let's, and we want to know, this question is calculate the fraction of the original charge that remains after the time is equal to the time constant. Okay, that's an equation, that's a question that I think is a reasonable question to ask. Okay, so what we would do is we would divide both sides of the equation by Q naught, right? So QT over Q naught equals E, and then I'm going to substitute in T equals the time constant, right? Because that's what it's asked me to do. It says where T is equal to the time constant, tau, which is just our resistance times capacitance, okay? So if I sub this in for T, it's going to be minus RC over RC, right? Which is just minus 1. So this will be 1 over E. So that's 0.37. So that would mean that here you've got 0.37 times the original charge at the time constant. Like after the amount of time that is equal to the time constant has passed, that's how much charge you would have left on the capacitor. That's how the time constant is defined. Does that make sense? Okay, I mean, all of this is just like, it's just definitions, right? I don't think there's any, the only sort of interesting physics is like this graph, in my opinion, right? The fact that it like, the amount of charge drops off exponentially. It's not linear. Okay, so let's try and find a let's do like a practical example. So we want to find an expression for the voltage. So like before we were looking at charge, the amount of charge as a function of time, right? That's what the previous plot showed. Now we want to look at like how does the voltage change as a function of time. Okay, so find an expression for the voltage across the capacitor as a function of time and sketch the voltage, like sketch what that plot would look like. Okay, so I know that there's like a certain potential difference, right? Because the top part of the plate, let's say, is positive and the bottom side is negative. And I'm like still, this is a continuation from the other situation, right? Where I've charged up the capacitor separately and I'm putting it into this circuit. So it's already charged when I start out with, yeah?
There's no like given assumption of like which side would have been charged positively.
No, like I don't, yeah, that's a great question. No, I wouldn't know that. It would, the only thing it would change is the direction of the current. Yeah, but you would have no way of knowing that like without like a meter, like a current meter or something. Okay, so I know that the change in voltage is equal to Q over C, right? But the thing is, we now know that Q is not a static Q. Q is a function of time, right? So I'm gonna modify this equation a tiny bit, and I'm just gonna say instead of just straight Q, I'm gonna say like Q as a function of time. Okay, so I know what that is, right? Because that's just the discharging equation, right? So it's minus T over RC over C, right? All I did was I substituted in the equation into Q because I know it's changing as a function of time. So at T equals 0, we know that E naught equals 1. So the change in voltage is just Q naught, like the original Q, over C. So if I were to graph this, it would look exactly like the graph the shape would be exactly like the shape that we had before, right? So on my y-axis, I'm going to have delta V, and here I'm going to have T, right? At T equals 0, so when T equals 0, what does the voltage equal? It equals like the full charge, the Q naught, divided by C, right? So this here, it's going to start from a point of Q naught over C, and then it's just going to drop off exponentially, just like the charge did. Okay, so we're going to have an exponential drop-off of V as a function of time. And it'll be the same exact shape, as the charge as a function of time, because they're mathematically related to each other. Okay? So now we want to find an expression for the magnitude of the current through the resistor as a function of time. And then we will be complete in terms of talking about discharging capacitors, right? So we know from the last page that the current as a function of time is just equal to negative QT over C times R, right? And using like the specific, it's like R2, like in my, specific to this particular circuit, right? And I showed that on the last page, right? So I know what QT is, right? It's just the discharging equation. So all I have to do is substitute that in. So it's negative Q naught times e to the minus t over RC over CR2. Okay, and what would that look like? Well, it's just going to look like an upside down function. It's going to look exactly like this function up here, but it's going to be upside down. So if that's current as a function of time, and this is time here, it's going to look like this, right? So like as t goes to infinity, what does current go towards? 0, right? The current starts out high. I mean, it's negative, but it's high, right? So it starts at t equals 0 when when at t equals 0, when you've got like Q naught, the current is high. So like another way to think of this is, you know how things move from high concentration to low concentration? If you've got like you've got these charged plates and there's charge packed onto them, and there's obviously a high concentration of charge, right? It's at the Q naught, like it's the fully charged situation. And then you connect it to a wire and you allow that current to flow. It's going to flow away from the highly concentrated current area, right? But it's not going to be linear. It's going to like, as you've got less current, it's going to drop off. The current will be less, right? So like as the plates become less charged, the current becomes less. Okay, so now let's look at the opposite situation, charging a capacitor. Okay, so it's exactly the same case, but now instead of allowing it to discharge through some electrical element, we're going to charge it up. Okay, so here we've got an uncharged capacitor, so Q is 0 to start with. Okay, and we connect it to a resistor and a battery in series, and we want to know what will happen, and we need to use the same laws that we just learned. So we're going to use Kirchhoff's laws, which the first step of that is always to draw a loop, right? So you know that current is going to flow like this, right? So that's going to be my loop. So the current is going to be like here, that, Okay. And, okay. So let's just apply the loop law. So if I start here and I go this way, this is going to be just E, right? The voltage of the battery. And then I hit this first resistor, and my current is going in the same direction as my loop. So it's going to be minus I times R1, right? And then who cares about the switch? And then I go to the capacitor, right? And my loop is in the same direction as the current through the capacitor. And so it's going to be minus Q over C equals 0, right? That's just the loop. So I1 is just going to equal the voltage of the battery divided by R1 minus Q over R1 times C. Okay? So we can show through calculus, we're not going to show you, that the charging equation is just this, right? It looks very similar, it's just the opposite to the discharging, right? So the maximum of Q max will be found when the current equals 0. Why does that make sense? Like, so you connect the battery and the resistor to the capacitor, right? And it charges up. And then once it's completely charged, the current stops flowing, right? Like, because everything is at an equipotential, right? So as soon as there's as much charge as you can pack onto the plates, there's no longer going to be current flowing. So if I connected, think of that experiment that I just mentioned. If this R1 was actually a bulb, it would be, so at first there'd be a lot of current going through it, and then the current would slow down. So you'd have a very bright bulb, right, when there's no charge on the plates. And then the more charge that builds up on the plates, the harder it is to force more charge onto the plates. And so the current is going to drop off. Okay? So I equals 0 when you have Q max. Okay? So we could actually sort of use our loop law. So when that happens, so everyone just look at this equation for a second. Okay. So, or actually it's maybe easier to see in this equation. I mean, they're the same equation. But so when the current stops flowing, this term here goes to 0. Does that make sense? Because there's no longer current going through the battery or through the resistor. So we can say that E minus 0, right? I've just substituted 0 for this because I is 0 in this term, right? If the current is 0 when the Q is maximum, then this term goes to 0. So E minus 0 minus Q over C equals 0. Then that means that E equals Q max over C, right? And Q max just equals E times C, C, which is the same as V times C, which is the equation that you already know. Right? So this is the case where the capacitor is fully charged. Capacitor fully charged. Okay? So this, number 3, so just take a couple of minutes to think quietly to yourself. Oh yeah, you have a question?
Yeah, for battery. Does E always equal V?
Yeah.
Okay.
Yeah. Good question. In the idealized, yes, yeah. Okay, so think about this question. What will the voltage across the capacitor be after a long period of time? So like I've got the capacitor, it has no charge on it. I connect it into this circuit, connect it to the battery and the resistor, and I leave it for a period of time. What will it eventually be equal to? You've got 4 choices. What do you think? Pardon? So when it's fully charged, what will be the potential difference across the capacitor? It'll be the same as the battery, right? That's why the current stops. When the battery and the capacitor are at the same potential, there's not going to be any current flowing. Yeah?
Is there anything that happens when the capacitor has like different properties than the battery?
The capacitor does have different properties of the battery.
But like, so what if the capacitor couldn't like take the full 9 volts? Then?
Oh, that's a great question. Yeah, you're totally right. The capacitor is whatever it is, right? Like the capacitance, like which is how much charge you can put on the capacitor, is a function of like the material and the area and the distance between the plates. But it doesn't have to take the full 9 volts. I mean, yeah, it's going to. I mean, remember you've got a resistor in there too. Like everything's going to be. It's going to stop charging once everything is at the same potential. Yeah, that's a great question. Okay, so the graph here shows like what happens when you're charging the capacitor, and it's the exact opposite from when you're discharging. Right? At t equals 0, so when t equals 0, the charge equals 0, right? And it's just the flipped upside down situation from what we just saw. So the RC, this is like 63% charged up, right? And it's got like 37% left to go. Right, that's the definition. It's the same definition. So this is like 37% of the original amount. Okay, like of like what, like it's still got 37% that it can take before it's fully charged. Okay, charge a capacitor, and so exactly what it means, like for a capacitor to be fully charged, and how the dynamics of that work. We sort of left off here with activity 8 pulling it all together, and I don't know if you had a chance to actually try this, but let's do this together. Okay, this is sort of just finishing up where we left off. So in many situations, as we've already seen, you can simplify an RC circuit before using like all of the laws, like the Kirchhoff's laws, by finding the equivalent resistance for both resistors and capacitors. So what we're going to do is we're going to analyze this relatively complicated looking circuit, and we're going to talk about what it would mean to charge this, to like basically close the switch and to charge the capacitors up. Okay, remember where we left off last time was we looked at what it means to discharge like a fully charged capacitor through a series of resistors. Now we're going to talk about like what does it look like if we have a not charged capacitor and we connect it to a battery and there are resistors in the circuit. What does it look like if we charge the capacitor up? Okay. So what would be the first thing you would do if you saw this circuit? What would be like the first step in sort of trying to analyze it? Pardon? Yeah, you'd find the equivalent resistors. So what I would do is I would first add those together, and so these are in parallel. So I'd say, okay, let's say that the equivalent resistance is 1 over R prime is 1 over R plus 1 over R, right? So R prime would be R over 2, right? and then you'd have like an equivalent resistor here, and then that would be in series with this one, right? So then second step, we would just add R prime and R, right? So the sort of overall equivalent resistance would just be R plus what I already figured out over there is R prime. So that's like R plus R over 2 is 3R over 2. Okay, so that is hopefully familiar at this point. So and then we would do the same exact thing with the capacitors, right? We would find the equivalent, like if we wanted to replace those two capacitors with one capacitor, what would that equivalent capacitor be? So we know that when you have capacitors in series, they add like this, right? We saw that last time, or 2 weeks ago, right? It would just be 1 over C plus 1 over C. So you would know that the equivalent is just C over 2, right? It would be like 2 over C and then the inverse of that to find the actual equivalent capacitance. Okay, so now next step is I would probably redraw it just to kind of like, because if redrawing it will allow me to apply my loop rules. Okay, so I would draw battery, and then it's got like a switch here, right? And it's got some R equivalent, which we just figured out, and then there is a capacitor, and then that goes back to the battery. Okay, so that's what that looks like. Okay, with the equivalent resistance and the equivalent capacitors. Okay, so the capacitors are initially discharged. Okay, remember last time we only dealt with the situation where we had a capacitor that was like magically somehow already charged up. And we looked at like what the function looks like if you allow that capacitor to discharge through resistors. So now we're gonna like look at like what happens when it charges up. So it's the exact same deal. You have to apply the loop rule. Okay, so I'm gonna draw a loop of the path that the current would follow if the switch was closed. Okay, so let me maybe change colors, although I forgot how to do that. Okay, so let me draw my loop, right? And then now what I can do is I can write an equation using all of the rules that you learned before, right? Like remember, if you go with the battery and then against the resistor and against the capacitor, and you add up all the voltages, what would it be? So let's say the EMF of the battery, the delta V of the battery, we're just going to call that E, okay, for EMF. So let's start with there. So like I'm going to go this way, right, like from here to here. So it's just going to be E, because remember that's the convention. If I go with, from low voltage to high voltage of the battery, it's just positive E, okay? And then I'm assuming that this switch is closed, right? Because that's the only way that this red loop is possible, right? Is if the switch is closed. So I mean, I could draw that just like that. Okay, so E, and then it's going to be minus I times R equivalent, right? Because remember, I'm going with, like, if you're going in the same direction as the current through a resistor, it's minus, right? Think back to those rules that we defined before. And then what's the voltage drop across the capacitor? Assuming I'm going with the direction of the current, it's minus Q over C. Nice, yes. Right, Q over C. Remember, delta V equals Q over C. Okay, so now I've gone like this way. I've gone across the capacitor. Okay, and that's going to equal 0. Right, because I'm coming back to the beginning. So remember, all the way around the loop, the change in voltage is 0. Okay, so now I can just manipulate this equation. Okay, so what's the goal? The goal is to find an expression for current as a function of time, for as the capacitor charges up. I want to be able to know, like at any given time, how much charge is on the capacitor. Okay, so I need a current function, like as a function of time. So I'm going to say I times R equivalent is equal to the EMF minus Q over C. Okay, but the Q is not a constant Q, right? Because I've written I as a function of t, I also have to write Q as a function of t, because we know that like as soon as I flip the switch, the charge on the capacitor is not constant. It's not like a given Q. It's like changing as the current flows to it. Okay, so the next step is I can just divide both of these terms by R, right? So I'm going to have, remember this is like my ultimate goal is to get current as a function of time. So I'm going to say that E divided by R equivalent minus Q as a function of t divided by R equivalent. And this is really C equivalent, right? I should, just to be consistent, I should write C equivalent. Okay, everyone with me so far? Yeah? Okay, and now all I have to do is substitute this QT for the function that I already know, right? If you look back to like 2 weeks ago, this is a function that I already know. This is the charging equation, right? Remember this is Q max times 1 minus E to the minus T over RC. Remember we talked about what RC is? Does anyone remember what we called RC? The time constant, right? Okay, so all I have to do is substitute that equation into this. Okay, so let's go ahead and do that. So I as a function of t equals the EMF over REQ minus Q max times 1 minus E minus T. And this is over R times. Okay? So, but what do I know? And this is going to require thinking back a little bit. What do I've gone off the page. What do I know about Q max? So I know that when the battery, when the capacitor is fully charged, when it's got like the maximum amount of charge on it, I know that is equal to what? Not 0. It's equal to, think of this equation. It's equal to the capacitance times the EMF of the battery, right? Which remember is just another word for V, right? So when it's fully charged, that means like it's the maximum capacitance, right? So what I could do is I could substitute in that C times the EMF for Q max, right? So if I do that, so this is E over REQ minus, so I'm going to just write that in, capacitance times the EMF times 1 minus E over REQ times C, okay? And that cancels out, okay? So if you do a little bit of algebra, and I probably should do this out. Yeah, I've got some room. So can you see that if I distribute the EMF through the brackets, I would get E over R equivalent minus E over R equivalent? Do you see that? Like so you've got this term, right, minus, and then I'm gonna, so E over R equivalent, right, and then this is plus, because I've got now like minus minus, right, so this is E times E minus T over RC over R equivalent. Okay, so these go away, right? Because they cancel each other, and then so your final expression is basically just this. So this is really useful because what it allows you to do is it allows you to plug in any time, right, and to see what the current is, right? To see like how much current is flown to the capacitor. Okay, is that clear? And this is an example of like, it's nice to see it once, but like you'd never have to reproduce it. Okay, it's just like we want you to see like where everything comes from. Okay, so is that good? Does anyone have any questions? No? Okay, so now we're going to look at sort of limiting cases. So what happens when t equals 0? What happens when t goes to infinity using that expression that we sort of just derived? Okay, so you've got, so find the current delivered. Well, why don't you guys actually try this? How many of you managed to try this? I know you were studying for the exam and probably doing the homework. And how many of you tried this like ahead of time? Nobody. Okay, so now that you've seen the expression derived, see if you can answer these two questions. What's this? Okay, forget that. So just E and F. Okay, see if you can like work together just for a couple of minutes and try to discuss the case, like what would the current be at t equals 0, and what would the current be at t when t goes to infinity. Okay, and then we'll pick it up in like 2 or 3 minutes. Okay, just like turn to the person closest to you and talk about it. Just to give you a hint, so remember, so don't be deceived. So this is like, this here is like, obviously, it's a beautiful equation, in that these two terms canceled out. But remember, it only works with the assumption that the capacitor is fully charged, right? Which is, of course, not true at t equals 0. Right? So like you can't actually start with this like very neat equation. You have to go back to like here, right? I mean, that just makes good sense, right? Because otherwise, how do you put t in? You can't just say, oh, right? So you'd have to kind of go from this point. Okay, so just try that. Hey, how's it going?
Good. Anything I need to either know or do for you?
I had some questions. Is this?
You're down.
We used to have something formal. Now we don't, but I can deal with it for you.
Okay, great. I was just wondering.
In a way that's consistent.
Okay, great.
And we'll talk about all the other stuff after.
Okay, great.
Do they know that they're getting rid of this back at the end?
Yeah, I told her. Okay, so let's see how you did. Okay, so let's go over the case where t equals 0. Okay, so let's start with the equation that the sort of the longer version of the equation, right? So we've got the current as a function of time is equal to the EMF divided by the equivalent resistance minus Q max times 1 minus e to the negative t over RC, okay, divided by RC. Okay, so let's talk about what happens to this part of the equation. What happens to this when t is equal to 0? It goes to 0. Is that clear? Is that obvious to everyone? Right? E to the negative 0 is just 1, so 1 minus 1 is 0. Right? So at t equals 0, the charge equals 0. That makes sense, right? Because you've only just closed the switch, right? So there's no charge that has accumulated on the capacitor at that point. Okay, so that's good. So Q at 0 at time 0 is just 0, right? I mean, another way to look at it is if we look at just that one part of the equation, right? This is 0 when this is 0. Okay. Okay, so the current delivered to the capacitor, it would just be a function of this part, right? Because the second term goes away. So this is sort of like having, it's like the capacitor is just a closed switch, right? So, like, do you understand what I mean by that? It's like the capacitor is sort of modeled as a closed switch. Right? It's like there's no sort of impedance to the charge that's building up on the capacitor because there's no charge there yet. Okay, so capacitor acts like a closed switch. Okay, so let's talk about the other contrasting case where t goes to infinity. Yeah. No.
So, like, I understand the concept that we kind of treat the capacitor like a closed switch when t equals 0. I understand what we just talked about, but I'm kind of confused by that at the same time because, like, nothing actually crosses the capacitor.
Yeah, but it's sort of like there's nothing. It's almost like you could replace the capacitor with just a straight wire at that point because, like, think of what happens. When as charge builds up, it becomes harder and harder for charge to flow to that. So when there's no charge, it has no problem flowing, right? As you build more charge on the capacitor, it's harder to put more and more charge there, right? Which is what sort of this expression is reflecting, right? It's exponentially, it goes down exponentially, the amount of charge that builds up as a function of time. So when there's no charge, it's just like there's like, it's like you can model it just as a straight wire where the capacitor isn't even there. Okay. Because I mean, what does this look like? Ohm's law, right? So when this term goes away, this part is just Ohm's law. Right? Okay. So the other case, I don't know, does that answer your?
Yeah, it's just slightly like mind-bending.
Yeah, yeah. No, definitely. Okay. Yeah. Okay. So what about the other case? So how does the current go when t goes to infinity? So when t goes to infinity, this goes to 0. Right? So like at infinity, the current stops. Right? And that should make sense to you too, because then that's the point at which you have the maximum amount of charge built up. So there's like, the whole thing is like an equipotential. There's no potential difference between any two parts of the circuit. So there's no current that can flow. Okay, so this is sort of like the capacitor acts like an open switch. Capacitor acts like an open switch. Okay, and something weird happens like with the, I don't know like why this like one paper. What is the time constant for this? I'll just write it over here. Just ignore, I'm not sure what happened there. So how would I calculate the time constant? Well, I just multiply, the time constant, remember, is like the amount of time that it would take to charge up the capacitor to like 2/3, right? Or 1/e to the full maximum charge, right? So I would just take, to calculate the time constant, I just multiply the equivalent resistance and the equivalent capacitance. Okay, so remember like on the previous page, we calculated what those two things were. We said that the equivalent capacitance is C/2 and the equivalent resistance is 3R/2. So it's really just literally a matter of multiplying those two together. So 3R/2 times C/2. So it would be like 3/4 RC would be the time constant for this particular circuit.